Welcome students. Today we are going to study the topic quantum yield, class M.Sc final chemistry, unit photochemistry. What is quantum efficiency or quantum yield? The efficiency of a photochemical reaction is usually expressed in terms of quantum yield phi, which is defined as it is the number of molecules undergoing chemical transformation per quantum of suitable radiation absorbed. Or we can say the number of molecules reacting per quantum of light absorbed. Basically, quantum yield is a relationship between the number of photons absorbed and number of molecules taking part in a photochemical reaction. Mathematically, phi is equal to number of molecules reacting in given time upon number of quanta absorbed in same time, or phi is equal to number of moles reacting in given time upon number of Einstein absorbed in same time. Or we can say phi is equal to rate of chemical reaction upon number of Einsteins absorbed. The energy E absorbed per molecule of the reacting substance is called 1 Einstein. The quantum yield of the product formation, phi, is equal to number of molecules of the product formed upon number of Einstein of radiation absorbed. If the law is correct, then the quantum yield should be equal to 1. If each quantum of light absorbed leads to the formation of product molecule, then phi will be 1. But in practice, it is usually less than 1 because of the decay of some light energy by fluorescence, phosphorescence, or radiationless processes. In the case of chain reactions, quantum yields may have value as high as several thousands. For several photochemical reactions, the high quantum yield is 10 to the power 6 and the low quantum yield is 10 to the power minus 2. Quantum yield of some photochemical reactions are shown in the table. You can see that for some reactions the value of phi is very high and for some reactions the value of phi is very low. Now let us discuss the reasons for low and high quantum yield one by one. So first we'll study the reasons for low quantum yield. Now the first reason is the deactivation of photoexcited species before chemical transformation. That is, the excited molecules may get deactivated before they form product. The next is recombination of fragmented intermediates. The dissociated fragments of reacting molecule may recombine to form the original molecule. Third one is the primary photochemical process may get reversed. And the fourth one is collisions of excited molecules with non-excited molecules take place during the reaction. In this process, the excited molecules may lose their energy and cause low quantum yield. Now let us study primary process and secondary process. In primary process, one molecule absorbs only one quantum of radiation and gets excited, as shown in the equation. In secondary process, after primary process, the excited molecules may de-excite, may decompose, or may transfer its energy to some other molecule. or may initiate a chain reaction. All these are secondary processes. The law of photochemical equivalence is restricted to primary photochemical process. That is, each reacting species excited by the absorption of one radiation gets chemical transformation and forms products and produces no further reaction. In such cases, there will be 1:1 relationship between the number of quanta absorbed and the number of reacting molecules. But in practice, most of the photochemical reactions undergo secondary photochemical reactions. That is, photochemically activated species or product molecule initiates a series of chemical transformations. While in some cases, photochemically activated species undergoes deactivation. They lose their energy in the form of heat or radiation. Under such conditions, there will be no more 1:1 relationship between the number of quanta absorbed and the product molecules. Now let us study the reasons for high quantum yield. The primary process of absorption of radiation produces excited free radicals, which initiates chain reaction. It causes high quantum yield. The next one is the formed product initiates another reaction. That is, with the formation of excited free radicals in the primary process, they undergo secondary process. Each secondary process again regenerates excited free radicals. This process continues until it is checked. Thus, by absorbing only one quantum of radiation, several reactant molecules undergo chemical reaction. Therefore, quantum yield phi will be higher than unity. The reasons can be explained in the following ways. The first reason is when the excited state of the molecule is quite stable. The excited molecule may collide with another molecule in the ground state and both may get decomposed, resulting in a higher quantum yield of the reaction. Example is shown here. Reactions are shown of NaCl. In these reactions, one molecule of NaCl absorbs one photon in accordance with Einstein's law and gets excited. The excited electronic state of this molecule is stable. This excited molecule collides with another molecule of NaCl and both get decomposed. Thus, with the absorption of one photon, two molecules of NaCl take part in the reaction. In this manner, the quantum yield of the reaction should be 2. Now let us study another reason. When the excited state of the molecule is above the maximum stability level or the excited state is itself unstable, the excited molecule itself dissociates into fragments, which set up a chain reaction. On account of this chain reaction, a large number of reactant molecules take part in the reaction without absorption of extra photons. This leads to a very high quantum yield of the reaction. Example, in photochemical combination of H2 and Cl2, a chlorine molecule absorbs a photon and gets excited to a level which is above the maximum stability level. You can see all the equations written here in the slide. In this level, molecule gets dissociated into free radicals. A chlorine free radical thus generated sets up a chain reaction and thousands of molecules of H2 and Cl2 combine together without any further absorption of photons. Thus, the quantum yield of the reaction is very high, of the order of 10 to the power 4. Next is, now let us study experimental determination of quantum yield. So to study the experimental determination of quantum yield, first let us study the experimental setup for the determination of quantum yield. The experimental setup for the determination of quantum yield is shown in the figure. First there is a source, then a slit, lens, monochromator, reaction vessel, and detector. So just have a look, draw this figure, and then we'll study this in detail. So first is the light source. For UV visible region of electromagnetic radiation, sunlight, arc lamp, mercury vapor lamp, discharge tube, etc. are used according to wavelength range needed for photochemical reaction under study. Next is monochromator. Monochromator works as a filter for radiation source. When light from source is passed through the lens and allowed to pass through it, it will absorb all of undesired wavelengths and transmit light of definite wavelength. Monochromators are generally made of gelatin or colored glass or transparent plates with metal films of suitable thickness. Next is the reaction cell. It should be of suitable size, made generally of glass or quartz with optical place windows for free exit and entrance of light radiation. Reaction cells contain reaction mixture and its material is inert towards chosen wavelength range. Next is detector. It is used for determining the intensity of light coming out of the reaction chamber. Now let us study the procedure for determining quantum yield of a photochemical reaction. So first is, we'll set up the apparatus as shown in the figure previously. Next comes the choice of light source, filter, reactor cell and detector. Depends upon the wavelength range used for the photochemical reaction. Now first keep the reaction vessel empty and allow the light to pass through it. Determine the light intensity. In case of solution, follow procedure by filling reaction cell with solvent. Now fill reaction vessel with reaction mixture. Allow the light to pass through it for a known time. and record the intensity of received light. The difference between the two readings will give the amount of energy absorbed by the reaction system under examination. Analyze the contents of reaction mixture. Now apply the following equation and put values to get quantum efficiency. Phi is equal to number of moles reacting in given time upon number of Einsteins absorbed in same time. The quantum yields of photochemical reactions are important because they inform us of the paths by which the electronically excited molecules utilize its energy. So it completes our topic, quantum yield. It is a very important topic and many times question is asked on this topic. So thank you so much.